Thank you, Sipto. I'm Ian. Unfortunately, the first author was unable to be here today, but we're all from the University of Pennsylvania Grasp Lab in the US, and I'll be presenting DFineNet, ego motion estimation, and depth refinement from sparse noisy depth input with RGB guidance. So as you're probably aware, there's a plethora of different depth sensors that are available nowadays, ranging from LiDAR, which gives very accurate long range but sparse depth, to sensors like structured light, which are relatively short range, only work indoors, but give you nice, dense depth. And really, the sort of ideal depth sensor is one that fuses the modalities from a bunch of these different sensors. We'd like dense depth over long ranges, over an entire image, so we get a really nice, crisp RGBD image. So this is an idea that's been around for a while, to fuse some kind of sparse depth sensor with RGB image data to come up with dense, sharp RGBD. And the key idea here is that the sparse depth is containing information about absolute depth value, and the RGB image contains information about depth discontinuities. So you should be able to do better than just simple interpolation by incorporating this RGB data. But purely, this pipeline is throwing out an important piece of information that we typically have, and that is time. So typically, as a robot is moving or as a vehicle is moving, you're gaining sequential depth and RGB images over time. And that contains structure for motion type information about depth, which we'd really like to capture. So we propose a network architecture which basically takes a depth prediction network and a structure for motion network and then fuses them together with a combined photometric loss. So we take in our ground truth depth, we downsample it for sparse depth, we feed that through pre-existing depth estimation network to predict depth, and we have another network based on SFM learner, which is predicting ego motion, and we use that predicted delta pose from the ego motion estimation and our depth that we predicted to project sequential images onto each other, from which we can then compute photometric loss. And because this entire network architecture is differentiable, we can then train both of these networks simultaneously. So to break things down into a little bit more detail, this is our loss function. The first term is effectively just sparse direct supervision, because we have these depth points that we excluded from our original input when we downsampled. We have the photometric loss, which we obtain by means of using the predicted ego motion estimation as well as depth to reproject, and then we multiply by an explainability mask to capture things like moving objects. And we have a smoothness cost to enforce local smoothness, which is essentially just the L1 norm of the gradient, and an explainability loss, which is there to prevent the explainability mask from just going to zero everywhere, trivially. So we use two primary data sets to benchmark our method. The first is TUM. This is a relatively old data set, came out in 2012 or so, from Connect sensors. So it's a challenging data set for depth completion, and particularly for classical monocular methods like DSO, because it's rolling shutter, Connect is relatively noisy, it's relatively short range, there's a lot of rotation in this data set, and often classical approaches fail fairly badly. We also use KITTI, which is very different, much longer range, LiDAR instead of Connect, which is a very different kind of depth sensor that gives you very different kind of information. And unlike the Connect, we don't have dense depth ground truth across the whole image, we only have it for a strip across the middle, which we'll see later matters somewhat. So this is some qualitative results from the TUM data set. Note in particular that the noisy depth, and we add noise to our data up to about, with the standard deviation of half the total depth. So we're able to very nicely smooth that out, and we're able to detect very nicely this desk in the background with a whole lot of detail that is not at all in the original image, and that's being extracted from the RGB data. Also here on the right, you can see KITTI. I particularly notice that at the top of the image, which is where there isn't any ground truth LiDAR data, other methods like Van Gutsbecke, who's at the time of publication was the first best performing method on the benchmark, cannot at all predict the region where there isn't any ground truth depth. Ma fails as well, but because we have this combined loss where we penalize this temporal stereo, we can still guess as to what that looks like. Here's some quantitative results. And again, the Ma and SFM learner are sort of the two key pieces of our network, and we are able to outperform both, which tells us that in fact this depth estimation problem and this ego motion estimation problem are coupled, and modeling them as such in our network structure increases performance. We're also much more resistant to noise if the network is trained with noisy input to begin with. So you see here that our RMSE error does increase, obviously, when we add noise, but not as much so as these other methods do. So we can use a wide variety of different depth sensors, from LiDAR to even like stereo, which is quite noisy. Quantitative results rather for KITTI. Again, the benchmark data can't capture the fact that we can infer depth for regions where there's no ground truth, because the benchmark is only interested in where there's ground truth comparison. You can also see here, so we can run our network with RGB data. We can also run it just with depth data. And we can clearly see that we can do actually reasonably well with just depth data. The network is in fact using information from RGB in order to improve our depth prediction. And then at the bottom is ego motion estimation results. Interestingly here, we don't do as well in terms of predicting translation and rotation error, but we do very well in terms of minimizing photometric loss, which makes plenty of sense because ultimately that's what we're penalizing in our loss function. Happy to take any questions. Thank you.